Hi, this is Prasanna from Wave Academia. In this video, we are going to discuss how to simulate three-phase inverter using Matlab. So in this three-phase inverter, two modes of operation are available. One is 180 degree of operation and another one is 120 degree of operation. So in this video, we are going to discuss how to do 120 degree of conduction in three-phase inverter. So in this 120 degree of operation, the conduction period of each switch is only 120 degree. So totally we are having, if you take a complete one cycle, we are having a 360 degree. So under that, the conduction period of each switch is 120 degree and only two switches will conduct at a time. Therefore, the two switches in the same leg of bridge have inherent deadband of 60 degree and there is no possibility of cross conduction. But if you take 180 degree of conduction, there is a possibility of cross conduction. So that will be overcome in 120 degree conduction mode. And here phase voltages are quasi square wave whereas line voltages are 6-step waves. Let us straight away go to the simulation, how to do that. First I will simulate the gate pulse and then we'll move on to the inverter circuit. For that I need a sinusoidal waveform. Okay, I'm going to take three sinusoidal waveform because I'm having three pair of switches. So I'm going to generate six gate pulse and then I'm going to take a sawtooth generator. So this is nothing but it's my carrier wave. So the frequency of sawtooth generator I'm using is 3 e power 3. This is nothing but the frequency of this three-phase inverter, 3000 Hz. So the first sine wave is compared with the sawtooth waveform and then it will produce the gate pulses accordingly. Now I can say that the first sine wave's value is, let it be sine type is time based, amplitude is 1, bias is 0. I'm going to change the frequency is 2 into pi into 50, and for the first phase let it be 0, and if you take the second sinusoidal wave, amplitude is 1, bias is 0, frequency is same actually, 2 into pi into 50, whereas here I'm going to change the phase, that is minus 2 into pi divided by 3. So each and everything should be, each and every waveform, every phases will be at 120 degree lag between each and every phases. Applying it. Take third one. Here also bias, amplitude is 1, bias is 0, frequency is same, 2 into pi into 50. And then here the phase I'm going to give is positive 2 into pi divided by 3. So we know that in this three-phase sinusoidal input, each and every phase will be 120 degree apart from each other. So 2 into pi divided by 3, that is the input value. If you take first sinusoidal waveform, the phase is 0. Second sinusoidal waveform, the phase is minus 2 pi by 3. The third sinusoidal waveform, phase is 2 pi by 3. Frequency is same, 2 into pi into 50. Frequency is same in all the criteria. So now this will going to produce a pulses. I can say that. So I'll tell you why I'm going to use not operator. I'm going to use some go to operator. I will tell you why I'm choosing this and all, this number of gates and all. I will tell you. I'm just copying the number of go to operator as a 6 numbers because I'm going to design a three-phase inverter with 6 switches. Okay, now I can say that this is S1. I am making the tag visibility as global. So make sure that tag visibility is global in all the cases, whether you are using a subsystem or if you are using a single page, what that doesn't matter. So it's a good practice. Apply it. Okay. Similarly, the invert of S1 is nothing but S4. Invert of S1 is S4. And then the second set of signal is nothing but it's S3 and S6. This one is S3 and the invert of S3 is S6. Make it as a global. And next set is S2, actually S5 and S2. Let it be, this one is S5. The invert of S5 is S2. Okay. So now the gate pulses are generated. Next step, I'm going to develop the inverter circuit, three-phase inverter circuit model with the switches. So here in three-phase inverter, I'm going to use 6 switches. So there will be 3 pairs. One pair will be conducted at particular period of time. So if you look at this, only 2 switches will conduct at a period of time. So since it is a it's having a six switches, so there will be three pairs of switches. Okay, accordingly, I'm going to trigger the switches by means of these pulses. So only I'm using not symbol. Actually, the invert. I want to create the pair, so I used not gate. Actually, I invert the signals. I need a DC power supply. Actually, inverter is nothing but it's a conversion of DC to AC. So I need a DC voltage source. That will be my input. Okay. And then I'm going to use six switches, that is IGBT. Okay, so if you look at this IGBT, it's having collector, emitter, gate, as well as M port is there. I don't want actually this M port. M port is applicable only if you want to measure the current through IGBT or voltage across IGBT and some other parameters regarding this switch. You can use this M port. As of now, I don't want this M port, so I'm disabling this one. Okay, now the M port is available. M port is not available. I will take this as a 6 number. Yes, now the circuit is connected. Now the switches are kept it like this. So I'm going to name the switch accordingly like this. This one is S1 and this one is S4. Actually, these two switches will work at a time. This one is S4. The inverter of S1 is actually S4. Okay, and then another pair is S3 and S6. And another pair is S5, and the inverter of S5 is S2 actually. Now you simply connect the switches accordingly. It will generate, it will create a three-phase inverter circuit. So now the input is given here. So this is your simple inverter circuit. You can trigger the switches by means of this gate pulses. The corresponding from tag I can take from go to. So corresponding S1 is given to the corresponding switches accordingly. Now if you want to measure the output, you can take three-phase power supply, three-phase output from each leg. So if you want to measure that either it's a three-phase current or voltage, I need a three-phase VI measurement. Okay. This is nothing but three-phase VI measurement. It's having input of A, B, C terminals and output of A, B, C terminals also there, and you can see that voltage of ABC and current of ABC is also available. In this case, I'm going to only measure the voltage, not going to measure current. So what I'll do, double click on it. You can make sure that the current measurement is no, because I don't want measure the current, so I'm fixing current measurement as no. Okay, if you want to measure the uh, phase voltage, you can go with phase to ground. If you want to measure line voltage, you can go with phase to phase. Okay, so both are possible. You can measure both line voltage as well as phase voltage. As of now, in this case, I'm going to measure only phase voltage, phase to ground. I'm applying it. Okay, so automatically this I ABC will go off. So now you can easily connect the each phase's leg. Actually, this circuit should be connected with a load, and that should be in closed loop, and that should be connected with the ground. So I need a three-phase parallel RLC branch. So we can directly connect A to A, B to B, and C to C. So in this three-phase RLC branch, I don't want RLC. I'm just going to keep only the resistive load, and the value of resistance is 1. Let it be. So after that, I'm going to short all the terminals of the output, and that should be connected with the ground. Now the simple circuit is over actually. If you want to measure the voltage, you can go with the scope. Okay, I need a Dmux because I want to separate all the phase voltages. Without using Dmux, it will give you all the voltages in a single scope. Okay, so I want to separate it accordingly. I'm keeping the number of inputs, number of outputs is 3. Similarly, in the scope also, I need a number of inputs, number of ports will be 3. The VABC is directly connected with the Dmux, and the output of Dmux is connected with the scope signal. That's it. Now the circuit is ready to execute. Only I have to do one more thing is I have to add the solver configuration. There is nothing but a power guide. Power guide is mandatory. Okay, so let it be power guide. So here this is the three-phase inverter circuit. This part which simulates, which generates the gate pulses to the inverter circuit, and this part is nothing but it's a three-phase inverter circuit with the switches. Number of switches is 6. Okay, now I already mentioned what is the input to the sine wave. Yes, and then the carrier frequency is 3000 hertz. That is nothing but the frequency of inverter. Okay, here I'm going to fix the input voltage. Input DC voltage is, let it be 150 volts. So this one is the input voltage, 150 voltage. It's a DC input. So what inverter will do? It will convert DC to AC. Fine. So here if you go to three-phase VA measurement, make sure that the voltage measurement is phase to ground. If you want to measure uh, face to face, that is also possible. Just what you have to do is you simply copy that part, connect it here. Okay, so this will give you line voltage. Okay, so the first, this scope will give you phase voltage, whereas this scope will give you line voltage of three-phase inverter. Let us see how it is working. Now if you run the system, so my stop time is 10. Okay, so now if you simulate the system, as we know that the phase voltages are quasi square wave, whereas line voltages are stick step waves. Let us see. If you look at this scope, and I'm going to view, going to layout, make this as a separate line. Similarly, take this one. Sorry. Go to layout. Put this as 3. So now I'm going to check first. I will check out with this one is phase voltage. Double click on it, expand it. This will give you phase voltages. Okay, accordingly phase A, phase B, phase C, all the 3 phase voltages are given here. So this is nothing but it's a quasi square wave phase voltages. Okay, now if you want to see the line voltage, double click on this one. So this is nothing but your line voltages are 6-step waves. Okay, 6-step waves. Suppose if you want to get a pure sinusoidal, what you can do is you have to add a compensator here. So let me take a transfer function. I'm going to do it for only one phase. I'm going to take a transfer function. So that transfer function is nothing but it's a compensator design. Okay, it's a compensator. So I'm going to fix 1 divided by, in this case I'm going to fix 0.01 to 1. That is nothing but it's a 1 divided by 0.01 s plus 1. I'm going to fix this compensator in between one of the phases. Okay, in between one of the phases. I'm going to convert the quasi square wave into pure sinusoidal wave, because if you take any inverter, the inverter itself they'll mention that it's a pure sinusoidal inverter. What it means, we need to convert that quasi square wave into sinusoidal. Okay, so now if you run the system, I'm doing it only for one phase. Okay, if you look at this, you will get a sinusoidal output for phase A. Phase B and phase C are quasi square wave. Phase A is actually a sinusoidal output. Similarly, you can develop your three-phase inverter like this in Matlab. It's very easy, and only thing you have to understand the concepts. Hope this video will help you to develop the three-phase inverter using Matlab. Kindly subscribe my channel and videos. Thank you for watching. Thank you very much.